Well, hello everyone. This video is designed to go over lesson 8.4, which talks about the Moivre theorem, powers and roots of complex numbers. So this theorem actually is the nth root of a complex number. It's very important because you're going to apply this in algebra as well, or in pre-calculus, and in calculus. So before I go in, I want to do a short review here in the corner. Let me see if I can do that. Just refreshing your memory a little bit on if you're dealing with a complex number. Say we have a complex number that we represent here in a plane. Yeah, and remember you have the real part and the imaginary part, right? So we have A and B, and here's the magnitude R, and here's the angle theta. Right, so A is the x component, yeah, which is R cosine of theta. B, which is the imaginary part, that is R sine of theta. And if you drop this down, you can see. Here's your A, here's your B, and that's how you look in a triangle. And R is nothing else but the magnitude of the complex number. So let's say our complex number Z is written as R parentheses cosine of theta plus I sine of theta. Yeah. And so R being the magnitude of Z, or the modulus as it's called, you find that by applying the Pythagorean theorem. So A squared plus B squared, square root of that. And finally, the position, tangent of theta, is given by the Y component, B over A, over the X component, where A is different than 0. This kind of captures everything in a nutshell, everything you learned so far about these complex numbers. So, now before we go in and we talk about it, the Moivre came up with this theorem where you have the exponent. If you're trying to raise a complex number to a power of n, that kind of distributes out the following way. The exponent goes to the modulus part, and then it goes to the argument part for each part of it, for the real component and for the imaginary component. Now you can write this short version or the compact version. In the end, it means the same thing. That is R to the n, parentheses, CIS, n theta. It's a very simple theorem, and I think it's easy to connect to it if you just raise a number to the second power. So typically, if you take, let's say, Z multiply with itself, and our Z right there, it's the same like above. If you write Z squared, it will be Z times Z. Yeah, so it will be R parentheses cosine of theta plus I sine of theta. Multiply that with, again, R cosine of theta plus I sine of theta. Yeah, so when you do that, as you can see here, you multiply R times R, so that gives you R squared, right? This R times R. Multiplication is commutative, so you get R squared. And then in a parentheses here, you have nothing else to do but to distribute each one of them. So cosine times cosine, that will give you cosine squared of theta. Then you have cosine times I sinus, so it's plus I cosine of theta sine of theta. I'm gonna erase this part right here for now, so we have a little bit of more room. Okay, and then so what I did so far, let's cosine times cosine, then cosine times I sinus, so we're done with that one. Let's take our I sinus, walk it through the parentheses. Yeah, so let's see what we get this time. So you get again plus I sine of theta cosine of theta. And in the end, you get plus I square sine square of theta. Yeah. So right now, what you're getting here is equal to R squared parentheses. If you're looking at this, let me see how I squared is 1. So you have the fundamental cosine square plus sine square here. That gives you a 1. Or I can write it as, let me put it in order here, cosine square of theta plus I square sine of theta plus 2I sine of theta cosine of theta. Okay, so when you keep solving this, because you can go ahead and continue with this, I'm trying to find room here to see where exactly I'm going to put it. But in the end, you will actually see that you end up with r squared cosine of 2 theta plus I sine of 2 theta. So let me see where I can put it in here. So we get the product theorem, actually. I didn't apply that. I should have. So if you apply the product theorem, which is in our previous lesson, let's make it simpler because this approach is more complicated. But if you apply the product theorem, then you get something like this. Let's erase that part and just make it with product theorem directly. Apply product theorem. Yeah, so we get r squared, and then you get cosine of the arguments. You add them, theta and theta, right? Those are the arguments for both numbers. It's theta 1 and theta 2. In this case, they're the same. Plus I sine of theta plus theta. I should have done that from the very beginning, I guess. Okay, so now what do you get here? R cosine of 2 theta plus I sine of 2 theta. Now look, that is nothing else but the theorem that's below. So the Moivre theorem says essentially is a multiple steps application of your product theorem that you already know from your previous lesson. So you distribute that exponent to the modulus R, and you insert that into the argument. Okay, with that being said, let's solve some problems here and see how do we apply it. All right, so the first one is square root of 2 plus I root 2. So in here, we pretty much have to see how exactly we're going to apply the theorem we just learned. So let's go ahead and see what's missing here. What am I missing here? If you look what you're missing here, you need to find R. Oops. You need to find R. And you need to find theta. Yeah. I mean, normally, because square root of 2 plus I root of 2 can be converted into some sort of a form of R cosine of theta plus I sine of theta. So that is our goal. Once we do that, we can apply the theorem above. And then after that, we have to write it back into the rectangular form. And so in order to find R and theta, we do R is square root of a squared plus b squared. So our a squared is root of 2 all squared. Then plus b squared is also root of 2 all squared. So now you have that. And if you look, that becomes square root of 2 plus 2, which is square root of 4, which is 2. Great. So we find R equal to. Now, what's the easiest way to find theta? As I said before, in our review right here, if you take the tangent of theta, meaning equals to the y component over the x component, well, we're going to do just that. Tangent of theta, in our case, is equal to root of 2 over root of 2. Those are actually equal. And that is equal to 1. Yeah? Now, because both of these a and b, so if you really look at it, right, or x and y, whatever you want to call them, so root of 2 is greater than 0. That's your a, yeah? Or your x, whatever. And also the other root of 2 is greater than 0, which is your b. Yeah, so that is your y, so that's greater than 0. That kind of tells you that the number has to be in quadrant 1. So theta belongs to Q1. Okay, so now you know that the tangent, if you look in quadrant 1, tangent is equal to 1 at 45 degrees. So we have theta equals 45 degrees. Great. So now we have both of these. So I can essentially rewrite my square root of 2 plus I root of 2 at the 5th power. I can simply rewrite it as, let's put it in a compact format, right? Because it's a little bit faster, I guess. 2 CIS of 45 degrees. And now I have to raise that to the 5th power. So that is applying the Moivre theorem. It is 2 to the 5th power, okay, times CIS of 5 times 45. That is my new argument. Okay, now if you do the math here, 2 to the 5th is 32. And then I'm going to put here parentheses cosine of 5 times 45 is 225. No, plus I sine of 225. Very well. Now, using the unit circle, you can depict how much is cosine and sine for 225. And so that becomes 32, parentheses. This will be a negative square root of 2 over 2 minus I root of 2 over 2 again. Now you can distribute your 32, and that simplifies with a 2 from the denominator. So you get negative 16 root 2 minus 16I root 2. I like to put the roots at the very end. So essentially, root 2 plus I root 2 to the 5th became 32 cosine of 225 plus I sine of 225. And then in the end, after you depict how much those are, it becomes negative 16 root 2 minus 16I root 2. Very good. So this is how you solve problems like that, and you can have different powers. You just have to pay attention to your math. And of course, depends on they are given to you, but if they are given to you in the format you had here, make sure you first find the modulus and also the argument. Very well. Let's move on to something else. Just a continuation of what you had so far. So this is called the Nth Root Theory. So in other words, you have a positive integer n, and you have a complex number, and you raise that to the nth power. Well, in the end, you obtain a new complex number that we're just going to call it x plus yi. So that is what we already learned above, and we did the example above. Now, what if you have to deal with the Nth Root Theory? You still have a positive n integer, and r is a positive real number, and you have theta in degrees. Then you have a non-zero complex number, which is r cosine of theta, r sine of theta. So let's say this time they give you the complex number that looks in that form, where you have r and theta involved. Then they ask you how many exactly distinct n roots you have. In other words, they ask you, can you extract square root of order n from such a number? And yes, the answer is yes, you can sure do that. And the way this has been proven is that it's going to be root of order n of r. And then you're going to have a new argument, cosine alpha plus I sine of alpha, where alpha, and this is probably the most important part, can be written as some sort of a multiple of the previous argument, going around the circle. So you have a theta plus 360k over n, where k is a number less than n by at least 1 unit. And then if you have it in radians, instead of 360, you can write 2 pi. Right? So 360 is equal to 2 pi, the same thing. And in the next, right here on the right-hand side, you just distribute the denominator. N distributes to theta, and n distributes to 360 times k, respectively. On the bottom, distributes to theta and the 2 pi k. Good. So this will be interesting to find out what are the 3 cube roots of negative 8? Now, before I do that, let me see if I can find this. I had this, I'm going to reload this for a moment, but in my iPad, it doesn't do the live. For some reason, the live demonstration doesn't work. But if I reload it, I want you to pay attention to what's happening here. So you see as n increases, you have multiple roots, and they kind of show on the screen. But then if I want to manually move this n to increase the number, it says start interactively, and it doesn't actually start. I tried several times, but you can play this on a computer. You can go search for Wolfram demonstration project and then plug in the nth root, and you will see what is happening. Essentially, you can have 3 roots, 5 roots, 9 roots, whatever it is, and they will show you on the screen how they look like. So it's kind of nifty to see that. So let's go back to our problem right here. So in our case, we're going to have square root of negative 8, but they ask you the 3 cube roots. And the question is, why 3? Well, why not 2? Right? Because, for example, 8 can be written as 2 times 2 times 2, which is 2 to the 3rd power. So this is just an observation here that's the reason probably they ask you that. So what is a cube root? Well, if you are looking at the theorem above, the Nth Root Theorem, you're going to have r cubed. And so you have to apply and see how you're going to rewrite this. Okay, so first let's start easy. I'm going to put here negative 8. And I'm going to go, well, how do I write this negative 8 so it appears in a form of a plus by? So it's negative 8 plus 0i. Very simple. 0 times I is still 0. So then I have to think of what number gives me, or what angle will give me this, or what argument. Well, let's look at it. R is equal to square root of a squared, which is negative 8 squared, plus b squared, which is 0 squared. Okay, if you do this math here, you get 8. Yeah, because negative 8 raised to the 2nd power, it will be 64 with a positive. Square root of that is 8. Good, now tangent of theta. Yeah, so the first thing I'm doing, I'm finding those to convert the number. Is the y component. Yeah, so let me put it this way. Y component over x component, just so you guys get used to it a little bit. So that becomes 0 over negative 8. Well, that is 0. Now you have to think, what kind of theta from here, if you look, theta is tangent minus 1 of 0, which is nothing else but pi. Now I put it in radians. So right now, if you are looking at negative 8 plus 0i, and we have r and we have theta, from these 3, I can say that I can rewrite my negative 8 as nothing else but, let's see, 8 parentheses, cosine of pi plus I sine of pi. So that is how to write it. Good, so right now we're gonna find out what are the cube roots. So I'm gonna highlight this because this is the part where we brought it to this format. So we have to look at how we calculate this, right? So first of all, we have r to the 3rd power is equal to 8. And so r is equal to 2, right? If you cube root it, if you extracted a root of order 3 of that, you get r equal to 2. Okay, and then alpha, if I'm looking at that, so we have square root of order n of r. We wrote it down, square root of order 3 of, in our case, was r to the 3, which was 8, yeah? And then our alpha, which is our new angle, I would say. Let's keep it in, I'm going to stay with degrees this time. I should have put there 180, but I'm going to do it now. So we have 180 plus 360 times k, okay, divided by 3. So I have nothing else, but I apply what it says on the theorem. Good. Or you can put it in radians, right? Pi plus 2 pi k over 3. Same thing. Very well. So we got all of this together. Now we're going to go back and have to look at the fact that you have to deal with k being 0, 1, 2, all the way to n minus 1. So my maximum k, because in our case n is 3, my maximum k will be 2. So I would say like this, just to stay organized. I'm going to say if k equals 1, then let's see what we get. Then alpha is pi plus 2 pi divided by 3, which is 3 pi over 3, which is pi. I should not skip k equals 0. Let me put k equals 0. If k equals 0, then what do we get? In our case, we get that alpha is 180 or pi over 3. So we have that. So we have one alpha as being pi, the other one is pi over 3. And finally, if k is equal to, which is the maximum that it can be, excuse me, alpha is pi plus 2 times 2 over there is 4 pi over 3. And that is 5 pi over 3. All right, so okay, and so to continue here, we got 3 different values for alpha. That means I'm going to have 3 different options for my roots. So let's write them down. So we have everything together to plug in and get our roots. So let's see, how do we write this? So the roots are, root of order 3 of 8 times, let's put it in compact form, CIS of pi over 3. That was for k equals 0, right? And now root of 3 of 8 is 2. So you get 2 CIS of pi over 3, which you can elaborate a little bit more. So that becomes 2 parentheses. Now you use your unit circle. Cosine of pi over 3, that's 1/2, plus I sine of pi over 3, which is root of 3 over 2. So that, if you distribute your 2, you get 1 plus I root 3. Okay, so that is 1 cube root. Okay, that was for alpha equals pi over 3. Let's see another one, and then another one here. Okay, the next one is root 3 of 8 times CIS of pi. That becomes 2 CIS of pi, which more so becomes 2. Now, cosine of pi is -1 plus I sine of pi is 0. So that term goes away, so you get -2. So that is your second one. Last one, root of order 3 of 8 times CIS. If k was 2, so that's 5 pi over 3. So that becomes 2 times CIS of 5 pi over 3. Okay, and that becomes more so if you use your unit circle. Cosine of 5 pi over 3, that's 1/2. And then the sinus of 5 pi over 3, let's see, that's negative. So it's negative I root 3 over 2. Distribute your 2 across, and you get 1 minus I root 3. And you know what's really cool? If you actually put this on a graph, they're evenly distributed, you know? So it will look kind of like, let me see if I can put a little picture here. So one of them is -2, and that is the real part. So it will be kind of like this. And then the other ones are kind of like that. They don't ask you to graph it, but one is 1 and root of 3, which is 1.7 something rather. So you can put it, represent 1.73. And then 1 minus 1.73, so it will be a shorter, a little bit smaller right there, because you get a negative number. But those will be the roots if you put them on the graph, okay? All right, so that's how you do this type of problems, but we'll continue with more examples and see how to depict each part of it and look at the condition of existence of these numbers. You know, I mean, it's very important for us to find out if they exist or not, right? Okay, very well. Let's move on. Here's another example. So you are asked to find the 4th root of this particular number. And not only that, they ask you to write them in rectangular form. So you kind of have to go back and forth and write them and use the unit circle and find out what they are. I'm going to make a table this time because I think it's nicer to have them in a table than written like that, but whatever works for you. So let's look at our number right here. So from -128 minus 128 square root of 3, you get that r is square root of -128 squared, yeah, plus, and now pay attention because there are two numbers in here. They are -128 and root of 3. They're all kind of together, so don't forget about the root of 3 now. So -128 root 3 all squared, and everything is underneath the square root. Now if you do the math here, you get 256. Great, so we get that r, our modulus, is 256. We'll keep that in mind. And now we're missing theta. For theta, remember, tangent of theta is the y component over the x component. So in our case, it's -128 root 3 divided by, but with a minus 128 also. So this gives you square root of 3. Now, if you look, what's important here, right? Both of these components, a and b, or x and y, right? So you can say x, which is -128, oops, 128, is less than 0. And y, which was -128 root 3, this is less than 0. So what is this telling you? This is telling you that because the tangent in here comes important to find out which quadrant you are, because both of these are negative, then theta or alpha or whatever you want to call it belongs to Q3. So now you know you are in Q3. So by using your unit circle, you will find out that theta is root of 3. Theta gives you tangent of theta of root of 3 if theta is 240. Good, so now we have everything. We have r and we have theta. So our number becomes, so -128 minus 128i root 3 can be written as 256 in a compact form, CIS of 240. Great. So now what we are asked to do, we are asked to do the 4th root, right? So the 4th root is important here. So 4 is part of it. So essentially you are asked to write this as, this must be equal to, I would say, some number to the 4th power, parentheses, cosine of 4 times alpha plus I sine of 4 alpha. So these two must be equal to each other. in order to be a root of it, right, a fourth root of it. So let's see what we get out of that. So I'm going to put this here like this, condition of existence. That means my r to the fourth must be equal to 256 for the new number, that is, right? And that means r is root of order 4 of 256. And you know that is 4. Okay, so we got that that's 4. And then what else do we get? We get that alpha, or I'm sorry, it's 4 alpha, because that's your argument, must be equal to 240, yeah, plus 360 times k. Do you see what I did? I made it easy. I put in the theorem there, they have this 4 that's right here. They have it divided by 4. I just kind of put them together because this connects a lot easy to what you're looking for, right? So I'm going to erase that part, okay? So from here, you can get exactly what it says, that alpha equals to 240 plus 360k over 4. Great. What are we looking for here? We are looking for k as being 0, 1, 2, and 3. So for each one of those, we need to actually calculate how much is alpha. But first, let's distribute a little bit. And alpha is equal to 240 divided by 4, that's 60. Plus 360 divided by 4, that's 90. And times k. So that is a way to look for alpha. And then we're going to plug in our k's. So this is where I said I'm going to make a little table, because I think it's easier to look at it if you have it on a table. And I'm going to do like this. R, which is the fourth root. And then I'm going to have k. And my k is 0, 1, 2, and 3. And then I'm going to write alpha, how much that is. Okay, so let's do like this. You will see how nice, if you have it in a table format, it's really, really easier to follow, I would say. So bear with me so I can do my lines here. Okay, so R is 4. Those are my fourth roots, all of them, all the time, right? And then for these, we get k 0, 1, 2, 3. So now let's plug in. If k equals 0, this angle is 60 alpha. If k equals 1, 90 plus 60, that's 150. If k equals 2, that's 180 plus 60, that's 240. Yeah, and then if k equals 3, so that is 330. Okay, now I will write like this. Fourth roots are, well, in a compact form, I can write like this. 4, because we determined that r equals 4, right? 4 CIS of 60. 4 CIS of 150. 4 CIS of 240. And 4 CIS of 330. Okay, so we have all of that. Now they ask us to write them in a rectangular format. So truly take your unit circle here. So fourth roots in rectangular format. See, in a previous problem, I just put those little dots and I kind of showed you 1, 2, 3 like that. But here, I'm sticking with a table. So let's see here, 4 parentheses. Well, cosine of 60, that's 1/2. And then plus sine of 60, that would be √3/2 I. And now if you distribute that 4, it will simplify. 4 over 2 is 2 plus 2I root 3. Okay, so that's the way to respond here. Next one, 4. Okay, cosine of 150, that's negative root 3 over 2 plus sine of 150, 1/2 I. This becomes, after you simplify it, negative 2 root 3 plus 2I. That's your second one. Third one, 4 parentheses. Cosine of 240, negative 1/2. Sine of 240, that would be negative square root of 3 over 2 I. Simplify, you get negative 2 minus 2I root 3. Okay, last one, cosine of 330, so you get 4 parentheses root 3 over 2 minus 1/2 I. Let's see, simplify, we get 2 root 3 minus 2I. And so that is how you find out the fourth roots of the original number or complex number that you were given, which was negative 128 minus 128 root of 3. All right, I have one more example before I close this. And then there will be the last lesson, and that will be 8.5. So let's look at the last example. This has to do with solving equations, because solving equations will imply that you find the roots, yeah? And here's an equation that you have to solve. X to the 6 plus I equals 0. And then in the end, they ask you to graph them as vectors, as I was trying to show you on that negative 8 or positive 8, I don't remember now, square root of that. So you have to graph them each vector in a complex plane. You know, in other words, if you are to graph them, you need to have the I and the R and the theta for each, right? It's kind of like graphing all of these. If you put them in a plane, if you look on the x coordinate, right, it's 2, for example, for the very first one I'm looking at, and then y coordinate, which is the imaginary point, is 2 root 3. So you take your calculator and say, okay, root 3, which is 1.7 blah blah times 2, and that will be on the y-axis, and you draw a vector. And that's pretty much what we're going to do here. All right, so let's see how we do that. So essentially, they ask you to find all complex roots. That is the idea. So find all complex roots. All right, so if I am looking at this equation, that becomes x to the 6 equals negative I. So now I am looking that there is a number right there that's raised to the 6th power that's equal to negative I. If I am looking at negative I and I want to write it as a plus bi, right? This is nothing else but my a is 0. I'm going to say 0 minus 1i. Having said that, now you can find your r. So my r right here, yeah, it is square root of 0 squared plus negative 1 all squared, which is square root of 1, which is simply 1. Great, so we find r equals 1. So that's great. Now we are to find theta, which you go by tangent of theta. Okay, tangent of theta, which is the y component over the x component. In our case, negative 1 over 0. So this is an error, right? So that's infinite. Your calculator will show you an error. So that's where you have an asymptote. So where do you have that? If you look at your unit circle, right, theta must be 270 degrees. Very good. So right now, we can actually rewrite our equation that was x to the 6 equals 0 minus 1i. We can rewrite it as x to the 6 equals r, which is 1, parentheses, cosine of 270 plus I of sine of 270. That's the equivalent form to write it. Now, this is where you apply the theorem again. The condition of existence of this to exist, right? You want to write down the 6th root. So I would say this must be equal to, so I'm going to change here to red, I'd say. So must be equal to r to the 6, parenthesis, cosine of alpha, or actually 6 alpha, plus I of sine of 6 alpha. So that is the condition of existence. What do we get out of that? Well, out of that, it results that if you start to identify what's happening here, right, r to the 6 equals 1, meaning that r is root of order 6 of 1, which still gives you r equal 1. So my new r is 1. And then you get that 270, yeah, 270 plus 360k must be equal to 6 alpha. So 6 alpha is 270 plus going around the circle, right? Plus 360k. Good. Then from here, we're going to pull out alpha. Alpha is 270 over 6 plus 360 over 6 times k. What are the values of k? So if you really look at it, it has to be 1 less than that exponent, yeah, which is essentially 5. So now you have to rewrite it. If I, you know what, let me simplify that. So this becomes what? 45 plus 60k. Yeah, that's much easier to use, isn't it? Okay, so we have everything we need for the r and for the alpha. Now we can make a table. Once we have the table, then we can actually put it up on a graph up there, okay? So in our case, let's see, my r equals 1 for all of them. Let me make it like this, r equal 1 for all of them. And so k is 0, 1, 2, all the way to 5. So I better have enough room here to make it 0, 1, 2, 3, 4, 5. So for all of these, my r is equal to 1, right? Then I have my alpha that I have to worry about. Okay, and after I have my alpha to worry about, we can write it as a solution set. Solution. Yeah, you can put those parentheses or not. Okay, so let's see what we have. When k is 0, then alpha is 45. When k is 1, then you have 60 plus 45, 105. When k is 2, that's 120 plus 45, that's 165. Okay, k is 3, then we get 225. K is 4, 285. Finally, k is 5, 345. That means you can rewrite them. Okay, let me redo this a little bit better. They don't say anything about the standard format, but you can write them like that as well. So this one is r is 1, and then you have, let's put them in compact form, CIS of 45. 1 times CIS of 105. 1 times CIS of 165. 1 times CIS of 225. Finally, 1 times CIS of 285. Finally, 1 times CIS of 345. And you know the good part about this is that you don't necessarily have to convert this into going back to the rectangular form, because truly what you do, this R here shows you that your so-called circle, right, has a radius of 1, right? And then the rest of it is just where the angle is positioned. So truly, if I am to go back up here and put all of this together, right? So 1, that means if I am to draw a circle here that has a radius of 1, I am going to be sitting on a radius of 1. So I'm going to attempt this. With the help of the iPad, I make it a nice circle. There it is. And so now I just go and put the angles. So at 45, so here's one solution, right? So I'm going to just call it CIS 45, because this is a 1 everywhere. Yeah, so this is a -1 and a -1. If this would have been a 2, then you make it a bigger circle, or you just make it like that and you call it a 2. Next one, 105. Well, 105 must be close to a 90, so let's say it's somewhere there. So CIS 105. Next one, 165, ceiling quadrant 2. So that would be closer to the 180. Okay, I guess leave it like that. So CIS 165. Next one, 225, right? Okay, so 225, it will be opposite of the other one. Let's try that again. So CIS 225. All right, and then we have 285, which is in Q4, somewhere here. Okay. Here we are. And the final is 345, opposite to this guy. Yeah, one is an extension of the other one. But here they are. We found all of them. 1, 2, 3, 4, 5, 6 of them. As we were asked, because remember, the power is at 6. When you have a 6 power, the power represents how many solutions you should get. Okay, some of them could repeat, but here nothing repeated. So there you have it. So I hope this was helpful. This covers lesson 8.4. And we'll see you soon in the next one. Thank you.